All right, here we go. Some fantastic answers for rational functions number two. Rational functions number two. I'm going to start on the back of the front page, the back of page one. Up here at number one, it says rewrite your answer for D, where the numerator and denominator are not factored but expanded out. So we should already have the answer in factored form from the front page. X squared minus 4 times x plus 1 over x plus 1 times x minus 2 over x minus 2. And now in order to multiply these out, I've got to pick two of them and multiply them together. So I guess I'll do the two fractions first. Now, when I'm multiplying my fractions, I just multiply across the top and multiply across the bottom. And remember how to multiply binomials and polynomials. You have to distribute, not FOIL, because when you FOIL, you're going to get yourself stuck here in a minute. So when I distribute, I'm going to get the same thing since across the top and the bottom I'm doing x plus 1 times x minus 2. So I'll get an x squared, and I'm going to get a minus 2x and a plus x. That's minus x, and I'm going to get a minus 2 over x squared minus x minus 2. And then I'm going to multiply by this x squared minus 4. So if I remember from way back in the beginning of the year, we talked about if I'm going to multiply one thing that's a fraction by something else, it'd be a good idea to write both of them as a fraction. And now for the top one, I have to distribute completely. I have to distribute the x squared from the first one to everything. And then I'm going to have to distribute the negative 4 to everything. And after that, I do some fun combining of like terms, and I will get x to the fourth minus x cubed minus 6x squared plus 4x plus 8. And on the bottom, I'm doing 1 times what I have, so it just stays the same, minus 2. Fantastic. Now we do the same thing for answer part E, 1 over x minus 2 times x minus 1 over x minus 1. And on the top, real straightforward, just get x minus 1. On the bottom, I've got to distribute everything out, and I get x squared minus 3x plus 2. Fantastic. The whole point of this section is for you to look at this note here. Interesting thing to note. These complicated algebraic expressions, let's pull the highlighter out here. This complicated thing here. So complicated. Look at it. It's got a fourth degree polynomial on top divided by a quadratic trinomial. Oh my gosh, it's so crazy. Super complicated expression. But what did that come from? Let's go scroll up real quick. That was graph D. Look back here at graph D. A parabola with a couple holes on it. And you came up with that equation just by knowing how to build it from a parabola, the x squared minus 4, and add the holes in here with these two factors. So what I'm really trying to show you here is that a super complicated algebraic expression, right there, like the one that is highlighted above, can yield a very simple looking graph. All right, so let's move on. Write an equation for a function that is a horizontal line with a constant height of 3, but a hole at x equals negative 2. Now, we've done a lot of examples of lines with holes at x equals negative 2. That shouldn't be hard. But now I want to do it with a line with a constant height of 3. So how about I think of this by thinking about multiplication of a couple graphs. So let's say I've got this times, boom. Let's start by putting on here the graph we want to start with without the hole. So that's a horizontal line at a constant height of 3. And now I want to, when I multiply this, I don't want to change anything about it. I just want to add a whole. So I want to multiply it by 1 almost everywhere, except here at -2, where I want it to be undefined. So if I multiply these two graphs together, I should get a line with a height of 3 and a hole at -2. Now, let's see if we can get equations. What's the equation for this line with a height of 3? Well, that's just y equals 3. What's the equation for this line with a height of 1 and a hole at -2? Well, that's just y equals x minus 2 over x minus 2. So if I got the graphs by multiplying, I sure as heck can get the equations by multiplying. Y equals 3 x minus 2 over x minus 2. Same as part A, only with holes. Oh, why didn't this one stay on the page? That's too bad. All right. Guess we'll just have to do the next one on the page. That's all right. Same as part A, but with holes at -2 and x equals 5. So I want to take that same graph from part A, boom, 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 height of 3, hole at -2, right there, and add a hole at 5. I don't want to change anything else. So I want to take it and multiply it by 1, except I want to put a hole way over here at 5. So what was the equation for this first graph? It was y equals 3 times x plus 2 over x plus 2. And this graph that has a height of 1, because I'm multiplying here and I don't want to change anything about this graph. I only want to change the hole. So this one with a height of 1 and a hole at 5 will be y equals x minus 5 over x minus 5. So for my answer here, I get y equals 3 x plus 2, x plus 2, x minus 5 over x minus 5. Cool. Write an equation for a graph that has x-intercepts at 1, at x equals 1, x equals 7, and a hole at x equals 3. So, x-intercepts. This is probably the part of the graph that we've talked about adding the least. We haven't spent that much time discussing it. So I'm going to tell you a couple different places in rational functions number 1 and number 1.5 that you can look for examples. So if you go back to rational functions number 1 and you go to the questions at the end, one of the questions said, when you multiply two graphs, when one of the graphs has an x-intercept, what do you know about the product graph? And what we said was that the product graph will have an x-intercept at that x value, the same as the original graph. And then if you go to rational functions number 1.5 and look at that, look at number 4, example number 4, you will see that we multiplied two lines and their x-intercepts became the x-intercepts of the parabola that we got as the answer. And finally, another place we can look for an example is if we scroll up here and look at letters C or D. I believe the answer, one of the ways we had it written for C was that it was x minus 2 times x plus 2 times x plus 1 over x plus 1. Now this x plus 1 over x plus 1, that gave us the whole at x equals -1. The x plus 2 right here gave us the x-intercept at x equals -2, and the x minus 2 gave us the x-intercept at x equals 2. So that's a little refresher, or some places you can look that will help us to see how to make these x-intercepts. So going back to the problem, I want an x-intercept at 1, so I need a factor of x minus 1. And actually, I'm going to write this in a slightly different way if my eraser works. Here we go. So I'm going to write it as x minus 1 over 1. Dividing something by 1 doesn't change it at all. But since a lot of the things that I'm using when I'm making these equations are fractions, I'm just going to go ahead and make this a fraction as well. I also want an x-intercept at 7. So that would be an x minus 7 over 1. And then I want a whole at 3. And we've done a lot of work with how to get that whole there. So an x minus 3 over an x minus 3. Okay, so this first term here gives us an x-intercept at 1. The second one will give us an x-intercept at 7. And then finally, a whole at x equals 3. Okay, number 5 here. It says write an equation for a graph that looks like this parabola, but has holes at x equals 1 and 3. So think about it this way. We want it to look like this parabola, but somehow end up being like the parabola, but with a hole, here and here. So can we make this a multiplication problem? Sure. We can add in a graph here that would be a constant height of 1, but have a hole there and a hole there. Constant height of 1 so that I don't change what it looks like. Add in the holes so that we get our final graph to have holes as well. So what did we multiply? Well, this one is x squared. This one is, I've got to get those 2 holes there. So that's an x minus 1 over x minus 1. And an x minus 3 over x minus 3. So my product here, my final answer is x squared times x minus 1 over x minus 1 times x minus 3 over x minus 3. Okay, we know that 1 over x plus 3 is a simple example of a graph with a vertical asymptote at x equals negative 3. So that right there is graph right here. This is y equals 1 over x plus 3. The vertical asymptote, that's this dashed line here, that the graph never quite reaches that line, and the actual value of the graph there is undefined. And you can see that by if you plugged in negative 3 in for x, you get 1 over 0. This graph over here is y equals 1 over x minus 3, because it's got the vertical asymptote at 3. And if I can see that because if I plugged in 3 here, I would get 1 over 0. And that would be undefined. Now, if I think about multiplying these two, and what's going to happen, I'm going to take values from this one times this one, from this one times this one. Think about what happens when I get to negative 3 here and I'm multiplying now. Well, this one's undefined. This one's something. Undefined times something. I'm still going to get undefined. So my product's definitely, my product here, boom, 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 is definitely going to be undefined at negative 3. But the same reason tells us is also going to be undefined at 3, because at 3, this one has something, but this one's undefined. So I think it'd be a good guess that, yeah, we're going to end up with 2 vertical asymptotes. So actually, let's, I'll open up my calculator software and we'll let that load, and maybe we'll look at that graph real quick. All right, we'll move on while that's loading. Now, how do you know that f of x will not have any x-intercepts? So x-intercepts occur when, what's the best way to say this? When we're dealing with these things and they're always fractions. Fractions, fractions, fractions. X-intercepts occur when, well, when we're dealing with anything, x-intercepts occur when y is 0. So y equals 0, that gives us an x-intercept. Okay, so let's say we have a fraction, numerator I'm just going to say num over denominator, then equals 0. How could a fraction ever equal 0? So a fraction only equals 0 ever if this equals 0. Numerator must equal 0. So in order for a fraction to equal 0, the numerator must equal 0. So look up here. Look up here, back here at this graph right here, this equation right here. Ooh, maybe my graph's open. Let's see. Oh, fantastic. Let's look at the graph first. All right, I'm going to put it in. It's 1 over x minus 3 times 1. Oops, I'll make it a fraction. Be extra careful when you're typing in fractions into your calculator. This, you have to make sure everything you want in the denominator is actually in the denominator. Your calculator can't read your mind. If you put 1 divided by x and then just plus 3 after that, it's not, that plus 3 will not end up in the denominator. Oh, cool, look at this. We've got an asymptote right here. We've got an asymptote right here. And if you count the dashes away from 0, you'll see we got asymptotes, vertical asymptotes there at -3 and at 3. Fantastic. And this thing, it looks like it's coming to the x-axis here. Like, look, it looks like it's getting close. In here, it looks like maybe it comes up and hits the x-axis here. Or maybe on this side, it's going to go hit the x-axis. Those would be x-intercepts where it hits the x-axis. But in order to hit the x-axis, I mean, our y value has to be 0. So let's go back to what we were saying. The numerator must equal 0. So look at this thing right here, this equation. This numerator is 1 times 1. It's 1. It's never going to be 0. It's 1. It just can't possibly be 0. So that's why, if I scroll back up here, when I was trying to find an x-intercepted -1, look at this. X-intercept is there because numerator equals 0 at x equals what? When x is 1, I get the numerator to be 0. So that will give me an x-intercept at 1. All right, that's why we just, when we're doing the x-intercepts, we just put something in the numerator that we want to be 0 to cause an x-intercept. All right, come up with an equation for a function that has 2 vertical asymptotes at x equals -2 and x equals 5. We've seen vertical asymptotes at a few different places. You can kind of think of this as, you know, the opposite of making an x-intercept. So instead of putting the term we want in the numerator, we put it in the denominator. So it's 1 over x plus 2. That'll give me a vertical asymptote at -2. And then I want to multiply it by the other vertical asymptote I want. So 1 over x minus 5. And we see that that gives us both our vertical asymptotes because we just did this example where we took our 2 vertical asymptotes. This was one at -3 and 3. Multiplied them together, and we got both of them, -3 and 3. Now, if we take our vertical asymptotes at -2 and 5, multiply them together, I'll get both of them. Okay, again, but with vertical asymptotes at -2 and 5, and a whole at x equals 3. So I've just got to take this same graph from the last problem, 1 over x plus 2 times 1 over x minus 5, and add a whole to it. So how do I do that? Well, I want to multiply it by 1, except at 3. I want it to be undefined there. So that's x minus 3 over x minus 3. Because that thing right there will most of the time be 1. When I plug in 4 in for this last term here, 4 minus 3 over 4 minus 3, 1 over 1. When I plug in 10, 10 minus 3 over 10 minus 3, 7 over 7 equals 1. But when I plug in 3, 3 minus 3 over 3 minus 3, that's 0 over 0, undefined. So that adds in the whole. All right, doing well, doing well. On to the challenge problems. Can you find the equation of a graph with x-intercepts at 1, 7, and a vertical asymptote at x equals 3? So if x-intercept at 1, that's x minus 1 over 1. X-intercept at 7, x minus 7 over 1. And then a vertical asymptote at x equals 3. That's 1 over x minus 3. If you're getting to this point in the video and maybe you picked up here because you already had done the first bit with your partner, but you're hearing me explain this and you're like, whoa, I don't really get where you're getting those from. Please go back earlier in the video. I spent some time explaining why these two terms will give you x-intercepts. I spent some time talking about why this will give you a vertical asymptote. So if you're here and you're unsure, go back and listen to those explanations in the earlier problems. Just start it from the beginning and replay things if you need to. Okay, challenge letter B. Well, x-intercepts at 1, 7, vertical asymptote at 3, and a hole at -5. So I've just got to build this equation up bit by bit. So x-intercept at 1 is an x minus 1 over 1. Boom, that has an x-intercept at 1. Now let's multiply by something to get an x-intercept at 7. How about x minus 7 over 1? Great. Now let's multiply by something to get a vertical asymptote at 3. 1 over x minus 3. And then finally, let's add in a hole at -5. So times x plus 5 over x plus 5. All right, and that's all I have for you today. If you get through this, go ahead and this section 3, go ahead and make your own problem that's similar to the problems in this section. And go ahead and bring that to class with you. We're going to use those. All right, have a good evening.